Hi guys, in this video, we're going to go over the Unit 2 Independent Task 3. So the 5 topics you had were probability, partial distribution, regression lines, hypothesis testing, and then probability distributions. So you should have already had a go at these questions, and you should have got to the level of support. So remember, if you get into like a level 1 and level 2, so you looked in your books or you watched the videos at the bottom of each question, then that's obviously quite a low level. So you probably just need a little bit of a recap and then have a go at a couple more questions. If you get into level 3 or 4 where you're speaking to a friend or a teacher, then you need to make sure that that is a topic that you're highlighting requires yourself a lot of work. Right, in question 1, okay, we're looking at a lot more WJC questions now. So I got the Venn diagram. So it's the subject studies studied by 40 sixth form students. F represents the studying French, M represents the set of students who study maths, and D represents the set of students who represent drama. The diagram is shown below. So here's my diagram here. Now you'll notice I've got some that overlap and some that don't, okay? So for example, F and D don't overlap, which means these two would be mutually exclusive, whereas M overlaps with both of them. So in the first question, okay, I've got explain what M intersection not D means in this context, okay? So this, in general, would mean M, but not D. So I'm just going to put that into context. That is a student that studies maths but not drama. Again, it's important there. It hasn't asked me for how many, like what's the number, what's the probability. It's just asked me to explain what that means. Okay, for the part B, that's when we're going to start using our probability. So one of the students is chosen random, find the probability that they study exactly 2. So probability to part 1 is probability of exactly 2. So if I want exactly 2, now if I'm forming this, obviously my denominator is going to be what there is in total, which is 40. Exactly 2 is going to be where they overlaps. So that's going to be 6 out of the 40. Now I can simplify I want, or if I can type in my calculator, but I can just leave it as 6 over 40 as well. For the next one, I want maths or French or both. Now, if I'm reading that, that's the same as me writing maths union with French. Okay, so I want maths or French or both. So maths or French would be the 10, the 13, and the 4, okay? Or both is the 2. So that would be the union between all of them. So what I'm going to do is I'm going to add up all these numbers, okay? So I've got 15, 19, so 29. So I end up with 29, and again, over 40. Now, part C is the long part of this question. Okay, I'll go on the next page. Determine whether studying maths and studying drama are statistically independent of each other. So we know to be independent, whether if I take the probability of M times the probability of D, okay, that will equal the intersection. So what I'm going to do is I'm going to work out what those three things are separately. So the probability of M, okay, is all my circle of M put together. So all my numbers in M, okay, which gives me 16. So that's 16 out of 40, which I am going to simplify in this case because it's going to help me with my timesing in a minute, which is 2 over 5. Okay, I'm going to do the same with probability of D. If I look at the full circle of D and I add them up, that's 10 over 40, which is a quarter. And I'm also, because I can do it, I can find what M intersection D is from my Venn diagram. So that's 4 over 40, or a tenth. Okay, so I've got those three things separately. Now I'm going to test it. So to test it, I'm going to do the probability of M times the probability of D. Okay, which would be 2/5 times 1/4. Now if I type that in my calculator, I get a tenth. Now I'm going to ask myself, does that equal the intersection? Which it does. So I'm going to say equals the probability of M intersection D. So therefore, studying mathematics and studying drama are independent. Okay, now let's say, for instance, if I got to this point here and I got, it was, I don't know, 3/10, I would then say, okay, that doesn't equal my intersection, so they're not independent. So it's important about when we can use a rule and when we can't. Right, so for the next one, we've got Poisson distribution. Okay, so in a study, a sample of soil were collected during the summer. Soil samples were in dimension of 25, 25, and 40 were collected for an analysis. The study found that there were, on average, 11 earthworms per sample. So per this area, per this volume here, there was 11 earthworms. So part A is explain briefly the conditions under which Poisson distribution could be used to model the number of earthworms per sample. Okay, so we've got a few things with Poisson distribution. Now, the key one, and kind of like the key defining difference between it being binomial or Poisson, is the fact that you've got a constant rate. So what I'm going to start with is that. So I'm going to say earthworms, okay, needs to occur at a constant average rate. Okay, now the other thing is they need to be independent. So they also need to occur independently. Okay, and there's my 2 marks. So there's my mark. I need to make sure I have both of those. Okay, the key word is being constant average rate, and independent is also really important. Okay, now obviously for binomial distribution, it also needs to be binomial, but with the constant average rate is what defines it to be a Poisson instead. Okay, so I've got in July, pupils at a primary school are asked to dig a smaller hole. So this is 25, 25 by 10. So you notice only the final number that's changed. Okay, so we can use that to our advantage. To count the number of earthworms, they find, okay, and then calculate the number of probabilities that there is exactly 5 earthworms. So first of all, I'm going to do my let x. I don't have a letter defined. I need to find it myself. So this is going to be the number of earthworms. Okay, in 25 by 25 by 10 centimeters holes. Okay, now I can do my x is Poisson distributed. Now I need to change my lambda here, because my lambda for 11, lambda of 11 was for 40. So I'm going to take 11 and I'm divided by 4 because I only want it per 10 now, because that's my last number. It gives me 2.75. So that means I've got x is Poisson distributed 2.75. Okay, now from here, I want the probability of exactly 5, so equals 5. Now, generally, said before, for Poisson binomial, okay, if it's equal to 5, you should be trying to use your formulas, okay? So I've got e to the minus lambda, so e to the minus 2.75, times lambda 2.75 to the power of your n, so 5, all over, in this case, 5 factorial. Okay, I want to type all that in, 0.0838. And again, we should check it using our calculator. We should try and use that formula as much as we possibly can to show off the skill. Right, so for part C, this is the hard one. Okay, we've got in the autumn, the average number of earthworms per sample is greater than the summer. Okay, so this sample was for the summer. I'm now looking at the autumn and they're saying it should be bigger than that. So my lambda should be bigger than 11. The probability that in the autumn there are fewer than 13 earthworms in the soil in the dimensions of 25, 25, and 40, which is the same as above, is close to 36%. So it's not necessarily 36%, but it's 36%, but it's close to it. Find the mean number of earthworms. That's find lambda, okay, to the nearest whole number per 25, 25, and 40 soil in the autumn, okay? So they've told me that the probability of it being fewer than 13. So that's what I'm going to use to my advantage here, okay? I know the probability of it being fewer than 13, which would be the probability, if I'm thinking about using my calculator, of being less than or equal to 12, is approximately 36%. Okay, so what I'm going to do is I'm going to use my calculator, okay, and I'm just going to use a bit of trial and error. So I'm going to use 12, and then I'm going to pick different lambdas to use here. Okay, now it has to be bigger than 11 because they told me that the average was bigger. So let's try 12 and let's see what it comes out as. If I do the probability of x being less than or equal to 12 when lambda is 12, I get 0.575, which isn't close to 36. Let's go up to 13 and let's see what it comes out as. Okay, that gives me 0.4631, and then still not close enough. Let's try 14 as well, which comes out as 0.3585, which if I rounded that would become 36%, isn't it? So that means, therefore, lambda must be 14. Okay, and all I've done is I just used a little bit of try and error. I've got this less than or equal to 12, so I can keep x as 12, and I've just changed my lambda as I've gone through. Right, now, regression lines. Okay, so you can see the really wordy question here, so we need to really make sure that we're understanding what's going on. Okay, so we've got a baker is aware that the pH of his sourdough Y and his hydration of X affects the taste and texture of the final product. The hydration is measured in milliliters of water per 100 grams of flour. The baker researches how the pH of his sourdough changes as the hydration changes. The results are shown in the diagram. So we go, we've got pH going in the Y direction. We got hydration going along the bottom. Part A, describe the relationship between pH and hydration. So it's 2 marks. So we need to make sure we're being clear here. Now, the first thing you notice is it's a linear relationship because it's going in a straight line down, isn't it? Okay, so that's the first thing I'm going to say. And it's pretty strong as well. So I'm going to do is a strong linear relationship. That's the first point I'm going to say here. Now, the other thing I'm going to describe is it hasn't asked for correlation, it's asked for relationship. So think about as one increases, the other either increases or decreases past that. Now, in this case, as hydration increases, the pH tends to decrease. Okay, so that's what's going to get me the 2 marks. So I've said it's a strong linear relationship, and then I've talked about what that relationship is. So as one increases, pH goes down, so it decreases. And there's the fact I've got the words tends in there as well. If I don't have that word, I'm potentially going to lose a mark. Okay, because it's not every point decreases as H increases. It's just about it tends to increase as I go along. Okay, so then part B, I'm going to do on the next page. Okay, so I've got B. I've got 2 parts. So I've got a regression line here of y equals 5.4 minus 0.02x. It wants me to interpret the gradient and the intercept in this context. Okay, so I'm not going to use y and x. Okay, x is what's going along the bottom, that's my hydration. pH is going at the side. So my gradient should be, as I go across one, I go up or down however much it is. Okay, so that's what I'm going to describe in terms of my relationship. So when I add 1 milliliter of water per 100 grams of flour. So that's my x direction. I'm going to describe what happens in the y direction. The pH tends to decrease, decreases, not tends this time, by 0.02. Okay, that's what that gradient tells me, 0.02. Okay, now there's no units, so I just leave it on average. Okay, it's not every point, it's just some points. That's just the gradient. Now let's look at the y-intercept. Now the y-intercept should be when your x is 0. So in this case, when the hydration is 0, of water per 100 grams of flour. Then the pH is 5.4. Okay, so another way to think about it is that the pH of the flour must be 5.4 because that's when I've got no water in it. Now, part 2, what it wants me to do, okay, it says estimates the pH of the sourdough when the hydration is 20 milliliters per 100 grams. Comment on the reliability of this estimate. So what I'm going to do is ask me to do it, so I'm going to have to do it. So I've got y equals 5.4 minus 0.02 times 20, which gives me 5. Okay, so that's my answer. That's what my pH would be. Now, I'm going to talk about how this is reliable or unreliable. So 20 isn't on my graph, is it? So it's not in my data set. So if it's not in your data set, it's unreliable. Okay, so I'm going to state that. Okay, this is unreliable. Okay, as 20 is outside the data set. Okay, if you've used the word extrapolation, that also works, okay? But that's basically me describing what extrapolation is. Right, question 4. We've got a hypothesis testing. Okay, and quite a difficult one as well when we get to part B down here. Okay, so the first bit is Dewi, a candidate in an election, believes that 45% of the electorate intend to vote for him. His agent, however, believes that this support is less than this. Okay, given that P denotes the proportion of probability, the proportion of electorate intending to vote for Dewi, part A, state your hypothesis. So H naught, okay, is going to be that P is currently 0.45, that's what he believes. And H1 is going to be, well, his agent thinks it's less than that. Now, they decide to question a random sample of 60 electors. They define the critical region as X being less than or equal to 20. So a critical region, remember, is the point at which I reject H naught. Okay, so I've got currently X. So X would be 60 and 0.45. Okay, they've already defined it for me, so I don't need to define it. Okay, they firstly want me to do is determine the significance level for the critical region. So that is simply me finding what's the probability of being less than or equal to 20. Okay, that's what the actual significance level would be. So if I use that, okay, that would be 0.0446. Okay, so that's the significance level I actually use for this question. Right. This is where things get a little bit tricky. So in fact, P is actually 0.35. Calculate the probability of a type 2 error. Okay, so you've got two types of error. You've got type 1 and type 2. Okay, so a type 2 error, okay, is not rejecting H naught, so keeping H naught. Okay, when we should have. Okay, so when the P in our case is less than 0.45. Okay, so the way we're going to work it out is, if I think about probabilities here, because I want to find a probability, okay, the point of me rejecting H naught is X being less than or equal to 20. So if I'm not going to reject it, that's X being greater than or equal to 21. Okay, but I'm going to use that X is now 60 and the new probability of 0.35. Okay, so I'm going to switch this around. So this is 1 minus the probability of X being less than or equal to 20, again, when X is. Okay, I'm going to slowly work out what this is. So I'm going to go to my calculator now, and I end up with 0.5484. That is my type 2 error. Now, part 3 wants me to explain in the context what this means, okay? So for part 3, I've basically got to explain what a type 2 error is in this context, okay? So type 2 error in this context is accepting that Dewi support is 45%. Okay, when actually it is actually 35%. Okay, so that's me doing the test and going, okay, insufficient evidence to reject H naught, so I keep it as 45, when actually I shouldn't have, and I should have gone, no, I reject it. Now, part 4, okay, says explain briefly why this testing is unsatisfactory. How could it improve while keeping approximately the same significance level? Okay, so the first thing is, why is it unsatisfactory? That's because if I look at the two probabilities, I've got 45% and 35%. That's a large error there. Okay, so that's why it's unsatisfactory. Okay, there is a large error in the probabilities. Okay, how to improve it, okay, is quite often the most really common answer, and it's going to be, it could be improved by taking a larger sample. Okay, so it could be improved by taking a larger sample. Okay, so we've got one more question to do. Okay, this probability distribution. So this probability distribution of X, the lifetime of bulb in hours is given. So I've got X going across the top, then you notice I've got a group table, and I've got probability going on the bottom. So suppose that a random sample of 40 light bulbs is tested. That's going to be really important, that number 40. And a histogram is drawn. Okay, so remember histogram, we should have frequency density going up the side. Calculate the height of the bar. So I need to find out what frequency density is for this group, which would be this one here. Okay, so if I'm planning ahead here, I know that frequency density is frequency divided by class width. Okay, now I know what the class width is quite easily. That's going to be 3, but I don't know what the frequency is. But I can work it out by using my probability. Okay, there's a probability of being 0.45, and there's 40 bulbs. So I can work out how many I would expect there to be. So that's 18. Okay, so now I can go, my frequency density is 18 divided by my class width, which is 3, which gives me 6 as an answer. Okay, so a nice little link there between your distribution and your histogram stuff. Right, Poppy, now suppose that the last two intervals is changed to 265 to 268 and 268 to 300. So you notice that only in between them at the moment, they got 267. So they want to change it. Explain why it is not possible to tell what will happen to the expected heights. Okay, so in this case, again, we've got group data. And this is a really common thing you would have dealt with in GCSE as well. If I've got group data, I don't know how the probability or the frequency is distributed between these two things. Okay, so I can't do things like that. Okay, so that's what we're going to say. We're going to say we don't know how the probability is distributed within the two groups. Okay, obviously we assume most of the time with these kind of things that they're all evenly distributed. So that we have, for example, if this was 10 people and this was 20 people, we assume that they're all evenly spread out. Whereas realistically, the 10 people in this first group could be all at the bottom end, and the 10 people, the 20 people in this group could be at the top, things like that. Okay, so it's important that we understand that we don't know the distribution here. So there's one more part of this. Okay, Clean collects a different random sample of 40 light bulbs. She draws the histogram of their lifetimes and finds that it is different to the histogram referred to in part A. Should Colleen be concerned about the two histograms' difference? Okay, so she takes a new sample and she finds it doesn't look like the one that she would have drawn if we drew everything up here. Okay, now she wants to know, should she be concerned? The answer is no. Okay, and it's because different samples will lead to a different result. Okay, they'll get a different probability, which means they'll get a different amount of lifetime for each bulb. Okay, so we're going to have no, because it's different, and you've got to refer to the fact it's the sample that's the issue, not the light bulbs. Okay, different samples will lead to different results. then you have to refer to the sample in here. You cannot refer to the light bulbs individually. Okay, so you should have marked that now. Remember to highlight anything that you need to go over. And apart from that, okay, we'll see you in the next task. Thank you, guys.